Okay, so very happy to have Michael Chapman talk to us. What is your title?
Linial Meshulam complexes. All right.
Linial Meshulam complexes. Okay.
Meshulam.
Combinatorics, group theory, and topology in one topic.
Yeah, that's the goal. Lots of topics. And I committed in my abstract not to assume any algebraic topology, and I'll try to stick to it. So you will learn, if you didn't know about certain notions from algebraic topology, you will learn about them today. If you did know about them, I'll do it quick and define everything, maybe in a way that you didn't see before, which maybe will be even helpful for those who know all the notions. Okay, great. So I have 2 weeks, and I'll talk about this topic for the next 2 weeks. And the general plan, so plan for 2 weeks.
Only 2 hours at a time.
Yeah, indeed, only 2 hours at a time. So the plan for 2 weeks is to talk first about connectivity. So this is today's topic. And next about expansion and stability. Expansion and stability. And this stability is related to the notion of locally testable error correcting code. So you will see, those of you who come more from computer science will see this is closely related to notions that you're used to from codes, and clearly connectivity and expansion are known notions. So this is the plan for the 2 weeks. Let me say what I'll do today. So plan for today. Before I do it, I'll just say I'm following 4 papers, okay? The first is due to Linial and Meshulam from 2006. The second is due to Babson, Hoffman, and Kale from 2010. The third is, so this is the first talk today. Next week, I'm going to talk about Hoffman, Kale, and Paquette. I think it's 2018, 19, no, this is 21, all right? And lastly, I'm talking about a work of myself with Yuval Peled, which is a preprint and already on archive. This is the plan for next week. And just as like highlights, this is like if you want to check and know, like if you know some of these stuff, I'm giving like those who are expert. This is talks about pi1. This talks about first cohomology with F2 coefficients. This talks about property T. And this talks about stability and sophicity. So this is just some name dropping for what happened in these 4 papers, but let's just talk about today. So the plan for today is first talk about the Erdos Renyi model. Erdos Renyi model for random graphs. Then talk about the Linial Meshulam complexes. So Linial Meshulam model for random 2-dimensional complexes. And I will say it can be generalized for higher dimensions, but because of the type of questions that we ask, we're only going to focus on the 2-dimensional case. And then we're going to talk about connectivity, 2 notions of connectivity, for these Linial Meshulam complexes. Okay, great. So let's start from the beginning. What is the Erdos Renyi model? Let's recall, because probably all of you have heard about it. Renyi. So a graph G, sampled according to G and P, where n is just a natural number and p is a number between 0 and 1, has vertex set, just the number between 1 and n. And every xy is included in E of G with probability P independent of all the others, independently of all others. So every edge I just asked, include it with probability P, don't include it with probability 1 minus P, do it for all n to choose 2 edges, you will get some graph, some random graph. And the first thing in the paper where they defined this notion, so this is Erdos Renyi from 1960. So the first thing they proved is that they found the correct P for which asymptotically the graph is connected if you're larger than this threshold and your graph is disconnected if you're lower. So let's write this formally. For any sequence of numbers that tends to infinity, no matter how slow, the probability that the graph G is sampled according to G and P is connected tends when n tends to infinity to 1 or 0. When is it 1? It's 1 when P is larger or equal to log n plus omega n. This is plus divided by n. And it's 0 when P is smaller than log n minus omega n, divided by n. So the number that I talked about is this log n divided by n. And we see that whenever you grow slightly faster than log n over n, you're connected with probability tending to 1. And whenever you grow slower than log n minus omega n divided by n, you're connected with probability 0. Again, when n tends to infinity. Great. And again, like you can ask, okay, what happens exactly at log n divided by n? People ask these type of questions, but this is out of the scope of this talk. Yes, so let's prove this. And again, like I'm going to give a proof sketch, and I know it's standard, it's like almost the first thing you learn when you do the probabilistic method kind of courses. But we will need it when we talk about Linial Meshulam because they do some generalization of this. So what is the proof sketch? So the case where P is smaller or equal to log n minus omega n divided by n. So in this case, you know that the probability that G is disconnected, okay, so I'm doing the complement of this number, disconnected, is bounded by the probability that there exists an isolated vertex.
Good.
Right?
The other direction.
Larger or equal. Thanks. You are right. And I'm trying to show that this is large, right? Yeah, it started in the wrong way. Perfect. And what is the probability that there is an isolated vertex? So you can do it carefully, but let's just say it out loud. Every edge is like choosing 2 uniform vertices. And you can check that when you're this distributed, you sampled n choose 2, about n choose 2 log n divided by n minus omega n. Many edges, right? That's about the amount of edges that you sample. So this is like collecting, you think of it as a coupon collector argument that you collect vertices, and you will see that in this parameter range, with probability tending to 1, you have an isolated vertex. That's exactly one part of the coupon collector argument. So this one tends to 1 by coupon collector. Perfect. So that's one side of the argument. What is the other side of the argument? The field larger or equal than log n plus omega n divided by n. Then the probability that G is disconnected, and now I am correct, and I'm going to do this in this direction now. Okay, so you can do a union bound, right? What does it mean that G is disconnected? That there is some empty cut in the graph. Okay. This make the 2 sets. Okay, so run over all sets S and S complement and N that are non-empty. Okay, and ask what is the probability that no edges between S and S complement, right? Like this is an empty cut in the graph, and this is a union bound. And this is just equal to the sum n goes k goes from 1 to n to n divided by 2 of 1 minus p to the size of sk times n minus k. And I need to add here how many cuts of this form there are and choose k cuts. Right, so I just wrote what is this number, okay? And now that's really quite a simple exercise. This thing, so I want to write it correctly. Yes. This thing is bounded by e to the minus omega n divided by 4, all of this to the power of k. So this is like a geometric, it's bounded by a geometric series with this quotient. So all of this stuff is bounded by 2 e to the minus omega n divided by 4, which tends to 0 as n tends to infinity. Okay, so this is just like usual Stirling type approximations and arguments. You get that. But the important part is that like you use a union bound and then you handle these types of summands in a maybe more careful way. Here it's only algebra. We will see that for linear Meshulam you need actually more careful way, and I'll get there. Great, so this is our just basis point. And now let's ask the following question. What does it mean? So we're going to talk about two-dimensional simplicial complexes in a moment. Simplicial complexes. And let's just quickly recall what it is. So a simplicial complex X with vertex set and is just a collection of subsets of n containing all singletons, So we want actually all the vertices to be in the vertex set. And if B is in X and A is contained in B, implies that A is in X. Great, so we have the definition of a complex just for good measure. And now I want to ask you, okay, like we define the notion of connectivity, like we know what does it mean for a graph to be connected. What would be a reasonable notion of connectivity for higher dimensions? So let me suggest to you two ways of viewing connectivity for graphs. So graph connectivity. You can view graph connectivity as no empty cuts in the graph. And this is completely equivalent to some notion from algebraic topology, which says that the first cohomology of this graph with any group of coefficients which is non-trivial is equal to 0. Okay, so let's assume this is a billion, this is 0. If this is not a billion, you will write here 1 or something. But the point is, this is equivalent to the first cohomology vanishing. Okay, and again, I'm not explaining this. I'm just saying, like, you can and we will see the definitions during this talk, and you will see that this is genuinely equivalent. But another way of viewing graph connectivity is just there is a single path connected component. There exists single path connected component. And in terms of algebraic topology, this is the same as the zeroth reduced homotopy of the graph vanishing. Okay, so let's write 0 as it again. Okay, so there is this notion of homotopy groups, and in the zeroth case, it's not a group, but it's just a set. And this is actually the set that counts how many connected components are there in your topological space, path connected components, and the reduce is just removing one of them. And it's natural to do this reduced thing. And essentially having a single path connected means that when you take the reduced thing, you get a vanishing thing. And now you would say, okay, I uploaded, so what is a simple graph? It's a one-dimensional simplicial complex. So what would be the analog of connectivity when you bump up the dimension by one, replacing, oh, this is zero, of course, sorry. Replacing these zeros by one. So upgrading the zeroth cohomology and the zeroth homotopy set to the first cohomology and first homotopy group. Okay, so these are two possible ways of upgrading the notion of connectivity to two-dimensional simplicial complexes. And I hope this is convincing that these are two ways of viewing the same thing, but somehow, like in the one-dimensional case, these are the same thing, but somehow in the higher dimensional case, these are no longer the same thing. So this vanishing and this vanishing are not the same property. Okay, great. And already Linial and Meshulam, you will see that the goal of Linial and Meshulam was to give this type of result for their notion of random two-dimensional simplicial complexes. And they chose they talked about these two options as options of defining connectivity, but they were only able to handle one of them. Okay, and we will see that in a moment. Okay, so now let's talk about the model.
That's now on the left in the sets out slash like you did say.
The two-dimensional means that the largest sets are triangles.
You define a general.
I define the general simplicial complex, but when you say it's two-dimensional, it means that the largest subsets are of size 3. And let's just have notations. All two-dimensional simplicial complexes have 4 kinds of cells. We have the minus one-dimensional cell, which is just the empty set. It has the 0-dimensional cells, which is just, we said by definition, it's all the vertices. Okay? It has x1, which is just the edges, so all sets of unoriented edges, just pairs of numbers between 1 and n. And it has the 2-dimensional cells, which are triangles. Yes.
Set containing the empty set.
I was just remembering Alex the Buck.
No, that's not true. The empty set itself is contained in every other subset of n. So you must have it in your simplicial complex. And it's very unique. It has 0 elements. So it sits somehow on its own in the space of -1 dimensional cells.
No,
Okay.
what I meant is that technically x minus.
You mean that x minus 1 is equal to, I meant that this is belonging to here. This is actually equal. You're right. I'm using different notations here. This is not an empty set, but it contains a single element, which is the empty set of the numbers between 1 and n. Great. After this minor technicality, let's move on. So what is the Linial Meshulam model? Linial Meshulam model. So now I'm trying to sample a calligraphic y out of y and p. And again, n is just a natural number, and p is a number between 0 and 1. Previous. And now you can look at the one skeleton. So the one skeleton of y is the complete graph. So what do I mean by that? This, like y1 contains all possible edges. Okay, you plug in all possible vertices, all possible edges. And the only thing which is random here is that each triangle, you either include it or not include it, and it will be independent with probability p. Okay, so every x, y, z is included with probability p independently of all others. So when I say included, I mean included in y2, the triangles and the stuff. Okay, great. So this is the Lineal Meshulam model. And because I want to have this type of theorem, I'm going to leave it on the board until we can define the proper notion. So let's quickly do a crash course in cohomology theory.
Homology, not cohomology, right?
What? Cohomology. Yeah, okay. Let's think about it just for a moment. Like in cohomology, use the word cocycles. And in homology, use the word cycles. So somehow when you actually encode something as homology, the objects will be cycles in the graph, like that's the way you should think about it. But when you do cohomology, what play the role of cycles is cuts in the graph. Okay? So when you try to talk about connectivity, you're talking about cuts, so the natural thing is talk about cohomology.
We do not have zero at the bottom, usually it's homology.
Yeah, the zero should be upstairs.
Ah, yeah.
Superscript.
Okay, like when I do cohomology, it's superscript. Yeah, I didn't remember that. Sorry. Okay, that's my bad on my bad notations. Okay, sorry. But still, I'm talking about cohomology. Let's just say it out loud. This is cohomology.
You first tell us what it is.
Yeah, that's what I'm going to do now. Now I'm going to actually define all the relevant notions. So let's do it real quickly. That we've done. Yes, let's talk about first cohomology. Actually, yeah, I'm not sure, like I wrote it differently. So let me do it a bit differently, okay? Let's still like just believe that there are these notions of cohomology. And let me write you the two theorems that I want to show you today. And then I'll dive into actually, so we know at least what is the Lineal Meshulam model. Now let's say what Babson, Hoffman, and Kane and what Lineal Meshulam showed. So the first theorem that I want to show today is due to Lineal Meshulam from 2006. It says the following: for every, similar to Erdos Renyi, for every omega n tending to infinity, the probability that the first cohomology, you said it's upstairs, I'll just follow your notations. So when y is sampled according to y and p, the probability that the first cohomology of y with f2 coefficients. So here we focused on a general, like we said that this is true for any group, but
We don't know what.
yes, that's okay. I will define it, but let's just say here something was very general. Here I'm just saying, okay, let's plug in a specific group. The specific group is just the numbers 0 and 1 with their regular mod 2 arithmetic, like addition actually. I don't need the multiplication. And I claim that this thing vanishes. This tends when n tends to infinity, again, to either 1 or 0. And this will be 1 when p is larger or equal to 2 log n plus omega n divided by n. And this is when p is smaller or equal to 2 log n minus omega n divided by n. So this will be the first part of the talk. I'll try to prove this. And the second part of the talk, I'll try to prove the following. So this is due to Babson, Hoffman, and Kale from 2010, as I said. And it was published then. It was uploaded to archive before. So here I need two things. So I need both for every n tending to infinity and every epsilon larger than 0. And you will see this will be a somewhat weaker type of result than this. So the probability that pi1 of y is trivial, which is denoted by 1 instead of 0, because this is usually a non-abelian group, when y is sampled according to y and p. Again, tends when n tends to infinity. Oops. And again, we have a 1 and a 0. 1 when p is larger or equal to square root of 3 log n plus omega n divided by n. And 0 when p is smaller or equal to n to the minus 1/2 minus epsilon. Okay, So again, I just want you to have the feeling this is very similar to Erdos Renyi's result. It's what's called a sharp threshold. We actually know the number for which if you slightly up or slightly down, we understand the behavior very well. Here, there is a very big gap. So you see, this is just n to the minus 1/2 times something logarithmic. And here it's n to the minus 1 minus epsilon for every positive epsilon. And actually, it's still completely open what is the exact place where it happens. There is some improvement. What?
It's known that there is an exact place. There is
It might not be
obvious.
sharp.
Yeah, maybe there is no sharp threshold. I don't know that it's known that there exists. I don't know that you can. Maybe it follows from something, but let's just. Yeah, I don't know. That's a good question. I want to focus on what the things that I know to tell you, but I will just say this was improved. So this was improved to larger than some constant times n to the minus 1/2. Like they dropped the polylogarithmic term by Luria and Peled in 2019. Okay, and they actually conjectured that they found the correct constant. So they conjectured in the paper that probably for everything smaller, so if you take a constant smaller than this C, you will be in this case. Okay, but they weren't able to prove it, and this is still the best bound that we have on this case. Okay. Okay, so this is not a sharp bound. Now, finally, okay, those of you who know what is fundamental group and one is the first cohomology, great.
The first result is doing any dimension, right? And
Yeah, but.
Okay, but that's not due to Linial and Meshulam, that's due to Meshulam and.
Voila.
Voila, okay,
That's D instead of T.
Yeah, okay, yeah, you need to replace this number, yeah. But still, I want to focus on two-dimensional because these type of questions are trivial for higher dimensional. This is like, okay, I'll just say it out loud. When I discussed this talk with Avi and Irit, like I think of linear Meshulam complexes as models for random groups, okay? Because this is a group that you can associate to the simplicial complex, and the simplicial complex is random, and this is a model for random groups. That is why I'm focusing on the two-dimensional case, because in the higher dimensions, the pi1 is always trivial. So somehow for me, when I'm thinking about the pi1 as the important object, and I do think of this as the important object, like, again, for my research, the most natural is the two-dimensional, and that's what I prepared, and that's what I want to talk about today, okay? But there are higher dimensional analogs of some of these results, and there are open questions in the higher dimensional analogs that are close in the two-dimensional case. I'll talk about co-boundary expansion at some point, that, like there are open questions in the higher dimension, but that are known in the two dimensions. So clearly there is a bigger story here. I'm focusing on the story that I brought. Okay, let's.
So you say like for higher dimension, pi1 will be trivial, is it?
Yes, just because you plug in all the triangles, and it's known that pi1 depends only on the two-dimensional skeleton of your CW complex, and in this case, the simplicial complex, and thus, like.
So for example, here in two-dimensional case, pi0 will be trivial.
You're right that in two dimensions pi0 is trivial. Why? Because there is only one connected component, and you included all the underlying graph, right? So clearly there is no disconnected parts in this graph. Yeah, you're right. I'm actually okay. Like there are higher dimensional analogs of pi1, and they are always abelian, and like you can ask the higher dimensional questions on pi, on the higher homotopy groups. But again, like I don't want to get into it. There is a higher dimensional story. Let's avoid it for this talk. Yeah.
Does it make sense to not include the others?
Yes. Yeah, it makes a lot of sense. Even you can ask, okay, let's sample from a GNP graph, and then, for example, look at the complete, like the flag complex defined by this. And I think Kale has, like Kale from Babsonov from Kale, has some works on this already from his PhD or something, and like there are actually he has a survey paper about various models for random simplicial complexes, And he has many like more geometric stuff, like more like this type of like, there is something very non-geometric about the GNP model in the sense that like every edge has the same probability, but you can somehow put your vertices first on a sphere and like say, okay, the probability that I include some edge depends on some distance on the sphere, and the probability that I include a triangle depends on some, like you can play all these type of stuff that actually like mimic some more geometric space behavior, and then different results occur. Again, Matthew has a survey paper on this, and I encourage those who are interested to check it out. Yeah, okay, great. Let's define cohomology. I'll bring my paper because I don't want to forget any important definition. This is 1, and this is 2. Great. So all I need is here. By the way, this constant is just, if you're interested, it's square root of 27 divided by 256. And it's related to some counting that Tat did about triangulations, in the plane. I don't know, like that's something like the inverse, like if you take square minus 2 here, it's some famous constant of Tat that is related to triangulations. So that's where this number comes from. It's not out of the blue, and they have some reason like that they think that this is the correct number. Okay, great. First cohomology. So what is the cochains? So these are the cochains. It's good that we take F2 coefficients. So that the thing here is F2 because it makes all the definitions much easier. Next week, I'll talk about general cohomology groups. And then I will recall some of the definitions because they need to change. Okay. But for now, we're in a good case. The cochains, the I cochains, are functions from the I cells to F2. And again, if I didn't say it enough before, F2 is just 0, 1 with mod 2 addition. Great, and this is a vector space. That's the great thing. If you choose a field as your target, you always get a vector space, and linear algebra is great. And then you can define the coboundary map. And this is from the I cochains to the I plus 1 cochains. And let me just give you the 3 ones that are relevant for us. So delta minus 1 of f of x. So when I start from minus 1 here, I move to 0 here. So delta minus 1 of f should define a function on vertices, given that f was a function only on the empty set. So it had only one value. So the only thing that I can write here essentially is f of the empty set. So it sends the value to the constant function on vertices with this value. Delta 0 f, again, the same game. If you start from a function on vertices, this should be a function on edges. This is actually just summing up the values on the 2 endpoints of the edge. Okay, so it's f of x plus f of y. And this is where F2 is nice. The natural thing is actually to orient the edges and take the endpoint minus the origin. That's what we're going to do next week. But because in F2 minus and plus are the same, just add it up, and you don't need to think about orientation and nothing. And delta 1 of f of xyz, again, the triangle has a boundary, just add up all the values along the boundary. F of xy, plus f of yz, plus f of xz. Great. We have that. Let's put it up. Now just check out that delta I composed with delta I minus 1 is equal to 0. So whenever you do one of them and then the other in a way that is actually well defined, you get the 0 map, okay, sending everything to the function which is constant 0. And these are actually linear maps. So can also check that. These are linear maps. So you can define two things. When I have a linear map, it's natural to define its image and its kernel. And this condition tells you that the image of this map is always in the kernel of this map. So the co-boundaries, the I co-boundaries.
It should be Li or delta I or delta I minus 1 because on the right you wrote doesn't match what thing that you wrote.
Why?
Because
First do delta I minus 1.
It's fine.
No, it's fine. It's fine. Yeah. This compiles. Check that this compiles.
It's
did.
delta I from CI to CI plus 1.
That's what I wrote, right?
it's
Plus.
Plus. Okay, when you see it here, it's clearly that it's plus. So it ups the dimension of the. But here you're right. This was not clear. Thanks. So it's C plus 1, I plus 1. So BI is the image of delta of I minus 1. And as we just said, this is contained in ZI, which is the kernel of delta I. And we call these the co-cycles. Co-cycles. And these are the co-boundaries. Like the I co-boundaries and the I co-cycles, if you want to emphasize what's happening here. And these are great. This is a vector space. This is a vector space. This thing is included in this. So you can just view their quotient as vector spaces. Okay, so you can define HI of your simplicial complex. I think it was X, my simplicial complex, with F2 coefficients, just to be defined as ZI modulo BI. And now we understand what does it mean to vanish. It just means that every element here, that this is an equality. So vanishing of this is the same as this not only being a containment, this actually is an equal sign. So homology vanishes, or homology vanishes when BI is equal to Z. And again, I'll just say next week, we won't have this notion of a quotient. Once we have non-abelian coefficients, this is no longer a group, but vanishing still makes sense. Okay, this property still makes sense when we have next week. This thing does not make sense. So I just want to emphasize it's now. Yes.
Can we put the I on the subscript?
Yeah, you don't like my subscript, sorry. I'm sorry that I mixed up the. I won't do it.
No, you.
The answer is no.
The answer is no. I'm sorry that I mixed up the upper and lower. I know that's not the standard. Okay, I didn't know that's not the standard. I forgot what is the standard I just chose. And let's go with it.
Anyway, you won't do any homology, so there won't be.
Right, you would not be confused by homology. Yes. Great, so we have all the definitions that we need. Now we can sketch the proof of, maybe I'll just give you an exercise. And the exercise is to check that what I wrote here before, it's already gone, on the notion of connectivity, that the zeroth cohomology vanishes with any non-trivial coefficients. Yeah, it does, it is here, thank you. I don't know, I'm not even looking well. My wife always laughs at me that I'm never able to find stuff, so you saw it now. Great, so just check that if you plug here F2 and you check what is the, okay, I'm using the bed notation, but what I defined here, no, the cohomology group, it is genuinely zero, and genuinely, let's just say that. So B0 will be just the constant functions, right? And B1 and Z0 checked, it's all the empty cuts in the graph. So it's all the ways of this cutting the graph into two parts such that there are no edges in between. So clearly, if the graph is connected, these are the same, right? Like there is no way, like only the constant, like taking everything in empty is a cut in the graph. Okay, great. So this was
Next week you're doing this one?
No. This is all already today. Next week, we're going to do property T and stability. So these I want to do both of them today. And for that, let's move on. So let's lift them up. So we remember that what we want to prove. let's pull this thing down and let's do a similar proof to the Erdos Renyi proof.
So you are not defining by what?
I know, I will define pi y once I prove something about pi 1, which will in the second part. So let's focus on linear Meshulam for now, because we defined this thing. We now know what is the first cohomology, and again, I'm sorry, I'm going to move this down, just because that's the way I'm going to write it throughout. And I'm sorry for that, I know I did a bad thing. But let's prove it, or at least sketch the proof. Proof sketch. So the first part is almost identical. So when p is smaller or equal to 2 log n minus omega n divided by n, the probability that the first cohomology of y with f2 coefficient does not vanish, y sampled according to y and p, is larger or equal than the probability y has an isolated edge. Isolated edge. What do I mean by an isolated edge? An edge that is not included in any triangle. Okay? And convince yourself, if I have an edge that is not included in any triangle, when I take the coboundary, it doesn't affect the image of the coboundary, right? Because the coboundary is just adding up the boundaries of triangles. So whether I put there a 0 or a 1 will not affect the boundary, which means that the cochain, which has the value 1 on this specific edge and 0 everywhere, is a coboundary, and it's not sorry, it's a cocycle. I'm saying the wrong word. It's a cocycle, but it's not a coboundary. Like it's coboundary, it is mapped to 0, but it's not the image of something from before. Okay, maybe let's just say what are even b1 of y. Okay, so I'll do it in a moment. Let's finish this. So I'm just saying, once you have an isolated edge, the characteristic function on this edge is a cocycle, which is not a coboundary. Okay, so this is like how do you say? Witness. This is a witness that this cohomology is non-trivial. Thank you. And again, like it's not exactly a coupon collector argument. It's like a second moment argument. Argument in spirit of coupon collector. So as opposed to an edge, which is essentially a pair of uniformly random vertices, a triangle is very far from being a triplet of uniformly random edges. Okay? So somehow triangles behave differently than edges, but still the proof of coupon collector still holds here. Just use a second moment argument and it works. And this tends to 1. Okay, so again, this part of the proof is very similar to the original Erdos Renyi. The other part of
Isolated edge means no triangles around that edge?
That's what I said. It's not contained in any triangle of y. So somehow when p is so small, there are edges that are not contained in any triangle, and then the characteristic function on them is a cocycle, which is not a coboundary, and this is a witness that the cohomology did not vanish.
And the 2 log n is really log of n plus 2.
Right. Yeah.
So that's the.
That's the reason.
Extra time to.
Yeah, exactly. Like this is, if you think of it as a coupon collector argument, that's the right, but I'm claiming it's a bit like, because triangles are not that free, you just need to be a bit more careful. You cannot just say coupon collector.
Slow you down, so.
Yes, sure.
For an isolated edge, it's clear that, meaning there's no triangles above it, so when you apply the coboundary map, it goes nowhere.
Right, because it's not included in any triangle.
But I still need to convince myself that it's also not a coboundary.
And we will do it in a moment. We will recall what are the coboundaries of the complete graph. So notice that
The graph
B1
is always complete.
B1.
You're not choosing edges at random.
Now you convince yourself, but I want to tell it to everyone. B1 is dependent only on the graph structure. And the graph structure is the complete graph in the Linial Meshulam case. So you just need to ask yourself, what are the coboundaries, the 1 coboundaries in the complete graph? And this is all possible ways like of taking a bipartite, like it's all the complete bipartite subgraphs of your graph. Okay. What? All the cuts, yeah, all the actual cuts in the graph. It's a bit confusing because before that we said that Z1 was the empty cuts. B1 is just all the cuts. Z1 was the empty cuts. So it's a bit Z0 was the empty cuts. Like, I don't know. It's a bit confusing. Do you call the cuts the actual two vertices or actually edges? But here I'm meaning the edges. Yeah. Yes.
Sorry, could you remind me of the details of the random model?
Yeah, the random model was take the complete graph and then you can stick a triangle wherever you want. Do it with probability P independently of all the others.
For each triangle?
Yeah, for each triangle. You have and choose 3 triangles.
Even like the overlapping ones? Yeah, okay.
There are no overlapping ones. These are independent events.
No, they overlap on an edge. And
Yeah. Like, okay, yeah, sure. Like, I'll and choose 3 triangles. Triangles. Include each one. With probability P. Yeah, independently of the others. So we have about P times n choose 3 triangles in the simplicial complex, right? Okay, great. So this was the first part.
Can you show like why you have isolated edges and this?
Why do you have an isolated edge? I claim that it's sorry.
Yeah. Why when you have isolated edge, the quotient is not 0?
Yes, so you need to convince yourself that the characteristic function of a single edge is not a coboundary.
I think you should do it slowly. I think it's.
Okay, let's do that.
maybe first compute the coboundary of isolated
Yes.
edge. The coboundary.
Okay, let me do it in the reverse manner. What is B1 of Y? So that's my first question. So I'm quotienting out by B1. I want to show you that something lives here and not here. That's my goal. So what is even this thing? So this is all functions f from the edges, okay, from n choose 2 to 0, 1 to f2. Defined as follows. So you take S, so let's call it f of S, where S is a subset of the vertices. Okay, and what is f of S? Fs of xy is 1 if x is in S, y is not in S, or vice versa, or y is in S, x is not in S, and it's 0, 0 otherwise. So every subset S, there is the complement of S. There are all the edges here. Just put 1 on these edges and 0 on all other edges. This is f of S. I claim that all of B of 1 looks like this. This is what Yotam called the cuts in the graph. Okay, but this is the edge cuts, like the indicators of edges, of all edges that appear in a specific cut. And clearly also like you have the full, all the set of all edges, right? It's also like the empty set and, actually no, the 0 set. And yeah, like if you do empty and everything, you get only the 0, the constant 0 function, for example. Great, okay, sorry. Why is the characteristic function of a single edge not here? I hope this is clear. If you take a single, so you have a huge graph, you have a single edge. This is the complete graph. If you remove this edge, you did not cut the graph into 2 pieces. The graph is still connected. It was the complete graph.
So n is at least 3. Okay.
Yeah, don't.
Okay, so
So n tends to infinity.
Okay.
N is huge.
Tell us something about the combinatorial meaning of Z1.
yeah, you should still say.
Yeah, okay. So let's think. What is the combinatorial? Actually, that's a bit of a confusing thing. Like, what is the combinatorial meaning of B1? It's easy. What is the combinatorial meaning of Z1? So clearly this now depends on the simplicial complex. Somehow we were lucky that Y had a complete one, like the one skeleton was a complete graph, then it was very easy to explain what is B1. But even in like, okay, that will always be like
You
these
can
cuts.
try it like this, for every triangle in your complex, you put an equation that leads the three edges to sum to zero. You want like an even number of edges. So Z1 is all the solutions, it's all the sets of edges that have an even number of edges on every triangle.
Yeah, okay, you can think of it as a code, that's what it is saying, right? This is a vector space, like the things that are mapped to zero are exactly like satisfying some list of, like a parity check. Like every triangle is a parity check, essentially.
So an isolated edge, it's in.
So let's think about an isolated edge is not, it's like a free variable in your parity check matrix, right? It's a variable that doesn't appear in any of the linear equations. So clearly it can be either a 0 over 1, and this just means that when you take the 1 here and 0 everywhere else, it is still satisfying, it's still in the code, right? Yeah, that's what it says. But it's not in B1. Yeah, that's important. There is a subcode for the code, and it's like we found something outside the subcode. Other questions? Okay. Yeah. Let's show the more interesting part. Like I know that this was an important discussion, but I genuinely want, like this was the easy part of the Lineal Meshulam argument. I want to move to the more interesting part. And here I need to define some more notions. So I'll do it here. That's this one.
I ask why
Yes.
we're looking at cohomology instead of homology.
What? Say
I ask why we're looking at cohomology instead of homology.
I tried to hint about it before. Like, if you check what is the which one tests cuts in the graph. So homology tests cycles, and that's the word cycles. But in the cohomology case, cos cycles are exactly cuts. So this connectivity is related to cutness and not to finding cycles in your, right? Homology will kind of count cycles, and cohomology will count like ways of disconnecting the object.
So if you want to generalize trees to either dimensions.
Homology, yeah. So yeah, I don't know, yeah. I hope that answers the question. So let me give you a few more definitions before I show the P is larger or equal to like the complement part. So for me, if I have a function from some probability space, it's a finite probability space, okay, to 0, 1, the norm of f is just what we usually call the Hamming weight, the normalized Hamming weight of this function, which is just the probability when I sample x that f of x is not equal to 0. Okay, so it's actually equal to 1 in this case, but you can generalize it to other target sets clearly. And this means that all these cochains have a notion of a norm on them, and this is the notion of a norm that I want you to take. And for every, this we've done, this is all cuts, we've done that.
So mu is uniform always or?
No, I didn't say that. Find probability space, this is well defined. Actually, we will need.
Coaches have a notion of, but what did you mean? What distribution do you think?
Yeah, so I'm saying that, okay, maybe for every measures that I'll put on cells of the graph, there will be an appropriate notion. You're right. I didn't say what is the measure on the cells. At some point, we will just give measure 1 to triangles, and edges will count how many triangles they are in. And that will be their weight and vertices and so on. Okay, great. So we already said that H1 of Y F2 is non-zero if and only if there exists some cochain such that, which is not a coboundary, such that its coboundary map is 0. That's just by definition. This is being in Z1 and this is finding something which is in Z1 and not in B1. Now, the problem is that this is too big of a set. So we are trying to mimic the Erdos Renyi result. In the Erdos Renyi result, you actually went over all cuts. you essentially went over this set. But you didn't really went over all this set because you always took S and S complementary simultaneously. So we actually, instead of looking at C1 mod B minus B1, we actually looked at C1 modulo B1. Okay, so remember, this is a vector space, this is a vector space. You can look at the equivalence relation. This subvector space induces on C1, and you don't need to check all of them that they give you like a non-trivial cut. Like the analog, the higher dimension analog of a non-trivial cut. You need only to use one from each representative set. So let's call Fn, so this is a notation from their paper. I think curly Fn. This is just C1 mod B1, but it's not all of C1 mod B1. Let's say it a bit more carefully. It's actually all the representatives, all the Fs in C1, such that for every H in C0, the norm of F of delta H is larger or equal than the norm of F. So out of all the equivalence class, and the equivalence class is defined by going over F plus delta H for every possible H, this is just the definition of the equivalent class. This is the one with the smallest norm, okay, the smallest Hamming weight. So I choose from every, like out of the cochains, I chose only those with minimal norm in their equivalence class. So that's the first reduction. I'm doing some reductions.
In this language, if it's an arbitrary function and you estimate the solution of your linear system, you estimate.
No, I'm adding the image of, no.
You had a cut.
You had a cut, sorry.
Yeah, it's not, I'm not adding a solution of the
Okay, you are adding a cut. So you're free to add whatever cut you want.
To minimize the norm.
Without having this.
Yeah, and I chose one of the minimizers. You don't need to choose, like clearly there is a single minimizer. There's not necessarily a single minimizer, so choose one of them.
So it's.
Yes, please ask.
Completely. And this representative is minimal with respect to this adding cuts.
Yes, okay, yeah, I'm a bit sloppy. You're right. There are potentially many Fs in the same equivalence class that have this property. I'm choosing one of them. Yeah, thank you. That's important. Now another simplification.
In Q1, I mean, how?
Yeah, I don't need it at this point, you will see. I'm just calling Fn. At some point, I will take the non-zero elements of Fn. Okay, but just to define Fn, it's all the representative, it's a representative system of the equivalence classes with minimal norm. Some set of representatives with minimal norm. Yes, I will say that at least the 0, 1 is actually the zero function. The representative of the coboundaries is actually the zero function because it's the only function with zero norm.
So that delta is delta 1.
What, say again? Yeah. When I write delta without actually writing, no, this is delta 0, right? So that's a good question.
No, I mean,
H was in C0. This is delta 0 of H. Now it's an element, it's in C1.
no, I mean the delta.
Here, this is delta 1. Yeah. You should understand from context. That's like the usual thing we do in cohomology theory. You should understand from context the indices sometimes. Maybe it's a bad habit, but at some point you have so many deltas that you just say, okay, understand from the context. Is it in C1? Is it in C2? Is it in C0? Then it should be delta 0, delta 1, delta 2, and so on in the respective manner.
Does the N and Fn just mean the number of vertices? Or
So the norm of F, we define it.
No, the notation Fn.
math cal f of n?
Yeah, that's called F of N. Is
What
for
is-
every element in C1, I choose a specific
What
representative.
is n signifying in the
Yeah, it's like the size of the underlying graph, right?
You
Like,
don't need it, really.
yes, okay, yeah. For us, this is F at this point, but yeah, I want to keep this notation just because it's consistent with the paper. The N is just telling me, okay, I'm in a linear Meshulam complex with N vertices. That's what it tells me. Perfect. Now I'm doing another reduction. So Fn prime is all elements of Fn elements of Fn that have at most one non-trivial connected component. What do I mean by that? The elements of F are indicators of edges, right? Some edges are in, some edges are out. So they induce graphs, right? So every function from the edges to 0, 1 induces a graph. This graph is usually it's many isolated vertices and maybe some more interesting connected components. Okay? Well, I claim that you can reduce the counting like we're going to do about. You can reduce the counting only to those that actually induce some connected component, which is interesting, and all the others are isolated edges.
Vertices.
Isolated vertices. Thank you. Yeah. Is that okay? And this is an exercise. It's not a hard exercise. It's kind of a infinite descent type of thing. Like if you had a counterexample, check that you can go down the counterexamples until, like if there is something in Zi, like in Z1, which is not in B1, you will find it out in Fn prime if it exists. That's the whole point. One of the representatives of Fn prime will already show you that.
You mean the minimal one, not...
Yeah, exactly. The minimal norm one will be in Fn prime. That's my claim. It's not clear. Like there is some infinite descent type of argument that you need to convince yourself is true. Like it's not a completely trivial exercise, but it is still a somewhat easy exercise. Convince yourself that this isn't big enough. If there is something in Z1 which is not in B1, already there is something in Fn prime, a non-zero element in Fn prime which is not in B1. Okay?
Can you repeat what is the non-trivial connected component?
Yes, like you may have, okay, like you look at your edges. They induce some graph structure, but maybe you have isolated edges, like isolated vertices that don't touch any edge. I don't care about these. Just look at the induced graph on the edges that you got. Forget all other vertices. Is it connected or not? Yeah. So that's what you include in Fn prime. Those that are connected in this case. And now let's try just right now what you need to show. So the probability that H1 of a linear Meshulam complex with F2 coefficients is non-zero is bounded by the sum over all F's in Fn prime that are non-zero. This is to you, Doron. So now I actually asked not to include the 0, 1 of the probability that delta of F is 0, right? Now, delta of F, like you can look at F in the complete complex. Okay, so so let me just add a notation. Delta Y of F is like the coboundary of F in the simplicial complex Y. Now you can ask yourself, how does delta of the complete complex, so I'm adding here a notation. This is the complete two-dimensional complex. So add all the triangles in. You can ask yourself, okay, this is not necessarily 0, right? Like unless F is actually, like we know that for every F which is not 0, this cannot be 0. So there are triangles that if they will be included into Y, they will ruin this condition. How many are there? Exactly the norm of this thing times the amount of triangles. So the probability that this occurs is exactly 1 minus P to this number. The norm of delta F, so the coboundary of F in the complete complex, times n choose 3. And now there are two key things that Linial and Meshulam do. Yes. I'm asking what is the probability that this happens. Now you should think of the Linial Meshulam complex in the reverse manner. Instead of adding triangles, remove triangles. So you remove a triangle with probability 1 minus p. How many triangles do you need to remove from the complete complex so that now the coboundary of F is 0? You need to remove all those that in the complete complex they are 1, right?
Yeah, but
This is the number of them just by definition.
The point was that inside Fn prime, you already know that it's not itself a coboundary. So in the complete complex, there will be some triangles
Yes.
that are turned on. That's what you said. And now you just need
Like my argument works even if this, but my argument works even if this is 0.
right. So
Yeah, I'm just saying in general, if you want to count like this probability is just in the complete complexes, in the complete complex, you look at the coboundary, you count how many triangles have 1 there. This is this number, just by definition.
they're the
And you
ones
just
that-
say you need to remove all of them.
these are
This is the probability of removal. Yes.
equations that witness the fact that F is not a coboundary. They-
Yes.
These are all the equations that will kind of be violated if F is not a coboundary. And in your
That F is not a cocycle.
No.
That F is not a cocycle.
F is not a cut. F is not a cut.
Wait. Like we're using 2 words differently. This means that F is a cocycle, right? This means that it's in the code. Like these are all the triangles that will take it out of the code, right?
What I said is something like this. F itself is in F, calligraphic F prime, meaning that it's not a cut. It's at least 1 edge away from a cut.
Yes.
If it was a cut, then all the triangle equations would be satisfied anyway.
Yes.
So it violates some triangle equations. How many? As many as you count there in the complete complex. And these are the ones that you need your complex to not contain. Because if it contains one of them, then F will show up as a non-cocycle.
Yes. Exactly. Indeed. So we're trying to ask ourselves, if I include this triangle, will it ruin this property? The answer is, these are the amount of triangles that will ruin this property.
Okay, so Fn prime is independent of y. I guess I was getting confused because there's delta 1 F.
So Fn prime is independent.
That's not actually in the condition of the set thing.
So Fn prime depends only on the underlying graph structure. It's independent of the actual triangles that I include. Yes, that's important. Yeah, it's independent of the 2-dimensional properties, only on the 1-dimensional properties which are fixed.
Also, Michael, maybe it's trivial, but maybe we're saying this explicitly, right? That in complete complex, all cocycles are actually coboundaries.
Yes.
So that's why kind of that's why.
Yes, I'm not saying that, but the cohomology of the complete complex, the first cohomology of the complete complex is 0. Yeah, that's what Yotam just said. This is vanishing for the complete complex. But I want you to at least understand that up until now, we tried to do something similar to the Erdos Renyi, right? We just needed something of this form, 1 minus p to some number for some collection of elements. This is a union bound. So the approach is very similar up until now. Maybe the accounting is slightly more complicated, but up until now, we did the same type of argument. Now you need to be a bit more careful. So how do you need to be a bit more careful? The other key thing that, so I'll stop in like 5 minutes for a break, and then we'll come back and try to explain as much as we can about Babson and Kale. So now they need 2 key properties that were missing completely in the Erdos Renyi thing. And I'm going to talk only on 1 key property. And this is a property of the complete complex, the complex with all triangles in it. So the key property is that for every element in F of n, okay, so for every minimal norm out of your coboundary class, equivalent class, the norm of the coboundary map in the complete complex is larger or equal to the norm of the original one. So this should be thought of as an expansion type of property. Okay, every edge, you look at its coboundary, like how many triangles it touches. So the minimal ones actually expand. how much do they expand? So if you actually do the counting, right, this is normalized by n choose 2. This is normalized by n choose 3. So actually the number of triangles that you touch are n divided by 3, as many as the number of edges that you had turned on. Okay, so this is, if you change the normalization to actually counting, instead of writing it in the norm form, you have n divided by 3 many triangles touching the edges of the original thing that will be lit at the end of this process. This property is called coboundary expansion. Boundary expansion. And they proved it a bit weakly, in a weaker form. They showed here 1/40, but it's not that hard to get the 1. And I want to just stop and say that's very helpful, right? Because it means that in this exponent, you can swap this number bit with f. And when you control this thing, in some cases, so you need to do case analysis. So for different sizes of norm f, you do different type of algebraic tricks. In some of the parameter setups, this is enough. Just replacing this number with the norm of f is enough for like 3 out of the parameter ranges that Linial and Meshulam play with. And for the third one, they need.
If you went to the 1 dimension less, then this would just be saying that the complete graph is a good expander.
Yeah, so I'll get there in a moment, okay? I'll explain what is, this is analogous to the Chigger constant in graphs, to the edge expansion of graphs, but I'll get there in a moment. So yeah, okay, maybe I'll write down the thing that I wanted to remark, and then we can move on. So the second thing I want to say, this is you should think about it as a co-isoperimetric inequality. Okay, so we are used to the fact that, like, what is an isoperimetric inequality? It relates, I don't know, the area of something to the circumference of it, right? Like it tells you some linear relation between these things. This is like the version of this type of property. And we will see that in the Babson-Hoffman-Kane, we will need a usual isoperimetric inequality. And in the proof of the other theorem, we need the usual type of geometric thing, and this is the of this usual isoperimetric inequality. And I'll just say that the proof for this without the 1/40 is quite, it's not hard, okay? So it's not a hard exercise to try to prove that for yourself if you haven't seen it before. Great, I want to say something about this property more. So Gromov rediscovered this property in 2009. And he understood the following property, that if a two-dimensional simplicial complex, I want to define the notion. So for a general simplicial complex, I will denote by H1 of the simplicial complex with F2 coefficients, just the minimum of a delta, what is it? So delta y of f divided by f when f are in these type of fn's. Okay, so for other subgraphs, you can still define fn, and you will define the appropriate fn, and you will have
prime, right, or something.
Yeah.
No, it doesn't matter. Doesn't matter. Just non-zero. Yeah.
Okay.
It's okay to take fn. Just the minimal norm ones. You don't need the connected. This is not relevant in the general.
Oh, okay, non-zero.
Yeah, just the non-zero ones. This is called the Chigger constant. This is the Chigger constant. And I will say that when you swap here the 0, this is again like just an exercise. This is exactly the edge expansion parameter of a graph. If you write here a 0, which is the usual Chigger constant that we think of in graph terms. So it is a higher dimensional analog of the Chigger constant. And what Gromov showed, that if a two-dimensional simplicial complex has, so maybe I'll write it differently. For every continuous map, Okay, sorry for that. For every continuous map,
Have a break.
yeah, in the break, I'll try to take it out. So from every continuous map from X to R squared, so just to the plane, and this is continuous, there exists a point in R2, which is in the image, of the Chigger constant times, so this should be an X because I just start from an X. The Chigger constant times some universal constant. This is universal. There is a point in the image of these many triangles of X.
Oh, this is
Yeah. This is the proportion, okay, which is in the image of
fraction.
fraction of the triangles. Okay, thank you. Fraction of the triangles of X. Thank you. That's very important.
So this
This is clearly a number between 0 and 1. Yes.
so F the input domain at x1.
Say again.
Like what is
This is a two-dimensional simplicial complex.
Yeah.
So how does the continuous map look like? Yeah, let's say that. How does the continuous map looks like? You first send the vertices somewhere, then every edge, okay, so you draw some vertices in the plane, okay, this is a plane, then you draw some edges. You can do it not in a straight line, you can do it in a manner like this, and maybe this, and then you just fill up the triangles. Just fill up the triangle. So this is not the most general continuous map, but it's the most adversarial continuous map. So for this question, these type of continuous maps are enough. You just draw the graph, but maybe with squiggly lines. And then whenever you see a triangle, you actually fill up this triangle. You can imagine that, right? Like whenever you have three such edges, fill up the triangle. This is
what
the
if
image.
they overlap like those curves?
That's okay. Here's another triangle.
Triangle
Wait.
itself has a lot.
Yeah, I'm saying like the three curve overlap.
Yeah, that's also okay. Like you can have this edge, and you want me to do like this.
Yeah.
Then okay, fill up.
That's the
This
triangle
thing?
with two edges.
What? Is it okay? No, it's okay. That's three edges. That's one edge. That's second edge. That's a third edge.
Okay.
Okay. Like just do the smallest part, which they actually cover as a triplet of like this works. Okay. Like there is a continuous map of this form from the simplicial complex to the two-dimensional place. It's plain, and these are the adversarial ones, as I said. Like these are the worst ones that for this property. But still, the point is that if your coboundary parameter, the Chigger constant, is high, there is a point which is covered by many triangles, by the images of many triangles. Now, this vastly generalized a result of Borosh and Faraday, which show that if you put just the vertices of the complete complex in the plane, and you draw all the triangles, all the possible triangles, there is a point that is covered by 2/9 of the triangles.
You put the edges as.
Now you do straight lines, like you are less free than in the continuous case. You actually draw the straight lines. There is a point which is covered by 2/9 proportion of the triangles. This is due to Borosh and Faraday, and Gromov was able to generalize it for the complete complex by just looking at continuous maps. So this is a much a much larger class of maps to the plane. And maybe you can try to, like, you should think of it like, okay, why can't I just draw all my triangles to be very thin? If all my triangles are very thin, it looks like I can avoid many points. But the truth is that once one triangle is thin, maybe this same edge participates in another triangle and makes it fat. Okay, so like what Gromov essentially tells you is that if you try to make them thin, you're never succeeding. Okay.
Generalize this in two ways. It's generalize it to any complex which has.
Yes, yeah. So I'm just saying that the one here And if you plug it into Gromov's machinery, it gives you the 2/9 of Borosh and Faraday, and clearly Gromov's type of result is much more general because it tells you something about all simplicial complexes, right? It gives you some lower bound, and this property of covering vertex many times is called topological expansion. So this says that coboundary expansion implies topological expansion. So this is one very famous application of this notion that popped up in the Linial Meshulam paper. Now I'm telling a story, okay? I'm not proving anything, and I'm not going to prove anything about the Linial Meshulam anymore. So now you want to bound this, you do some tricks. This is one of the tricks. There is another trick, which is more like a small set expansion type of trick, but I'm not going to talk about it at all. I want to say just one last thing, which is relevant to this audience, and it's that just recently, I don't know, in the last 2 years,
Before, this may seem really weird why you call it topological expansion. But if you look at the graph case, and you have one simplicial complex, and this will be just mapping your vertices to a line, and you want that there exists a point that cuts a constant fraction of the edges. This is almost like expansion, except for if you have some isolation.
Yeah, so it's essentially having a large component, which is an expansion.
Component, which is
Yeah. Like this is like weaker than expansion, even in the one-dimensional case, but not much weaker. It tells you that there is a big connected component in the graph, which is a good expander.
That's the reason for calling.
Yeah.
I don't agree. Is that
Like maybe you need to cut some. Sorry, right? You need to be even a bit more careful. You can have like two very good expanders and connect them by an edge. This is still expanding in this sense. So you need to be a bit more careful. It kind of says something. Yeah, it's just a weaker notion. Yeah, no. Like it's not immediate that it's the same.
But every expander has this notion.
Yeah, usual expansion implies this topological expansion in one dimensions, and this is the two-dimensional version. And again, some very strong notion of expansion implies it. So this should be thought of a very strong notion of expansion. This is the expander. And I'll just say some amplifications of boundary expansion were recently used to construct polylogarithmic, quasi-linear DCPs with small soundness. And this is a sequence of works. So Elite with Yotam and Alex Lubotsky. This is one of the works, and Bafna and Lipschitz and Mintzer is another work, and Bafna, Mintzer, and Yas, I think, is another work. So there were recently like just take this notion, essentially replace this F2 by some finite collection of finite groups, but some bounded finite collection of bounded groups. And then if all of them have this property, with all of these coefficient groups you have this property, then you can somehow construct PCPs. And agreement testers, right? How do I say it? Right? So that's another part of the story. And let's take a break. I know that, and I'll do half an hour from 12 to 12:30 about the Babson-Hoffman K, which is the other thing I wanted to talk about. Great. So we saw some of the argument of the Linial Meshulam, the hard part of the Linial Meshulam theorem, and I claim there is another sneaky trick, but essentially we saw at least the idea, the form of the proof. And now I want to talk about the Babson-Hoffman K, but for that we need to recall what is the fundamental group of a simplicial complex. So to that end, I'll start with what is a Van Kampen diagram. This is a very important notion, a Van Kampen diagram. So this is a diagram that you draw on the board, on the plane. And it always looks something like this. So you have some disks, They are connected with some paths between them, and maybe one of them has something like that. So it's essentially a simplicial complex that you draw first the boundary of. And then whenever you see a disk, you need to triangulate it. So there are some triangles that fill up and add more vertices, and then it will be easier to draw triangles. And so on and so forth. So you triangulate all this disk, and you triangulate all of this disk, and you triangulate all of this disk. And up until now, it's unrelated completely to the simplicial complex we started with. But now you write numbers. So you assume that the simplicial complex had vertex set 1 up to n, like before. And just start writing numbers on these vertices. So maybe that's x1, and x1 is one of the vertices of the original complex, and this is x2. And this is x3, and maybe here x1 appears again, and this is x4, and so on and so forth. And this will be a Van Kampen diagram of the original complex if after you wrote down all of these vertices, the names of all of these vertices, whenever you see an edge, it's actually an edge from the original simplicial complex. And whenever you see a triangle, it's actually an original triangle from the simplicial complex. So here I see this is x4. So here's x1, x3, x4. If you see this picture in the Van Kampen diagram, it means that x1, x3, x4 is a triangle in the original simplicial complex. This is what it means to be a Van Kampen diagram of a simplicial complex X. And now there are a few parameters associated with the Van Kampen diagram. So first of all is like the boundary. So I'm denoting this diagram as D. And these after I put the numbers of the vertices, okay? So the boundary of D is just the path, so it's not well defined. It's well defined up to deciding on a starting point. But let's fix a starting point, okay? Say that this is a starting point.
The diagram is connected?
Yes. It must be connected, and it must be like homotopy equivalent to
You
a
also have
form.
vertices on the edges, right?
Yes. These are paths. These are paths, like maybe there's a vertex here, a vertex here. This is a path of length 3. This is a path. So, but the point is that you write down the paths, and then you just write numbers like the vertices from the original simplicial complex, and now it deduces a few parameters out of the Van Kampen diagram. The first one is its circumference. So we actually need to decide on the starting point and the orientation. Let's say that we always orient clockwise, okay? So from here, I will go x1, x2, x3, x1. So I will read this path, you see? I'm going around everything, and I'm always going clockwise. I think I'm doing clockwise. And I get back. You agree that this is a closed path? This induces a closed path in the original simplicial complex. It's just some path in the underlying graph of the simplicial complex. This is called gamma. This is the circumference of D. Okay. Now there are two other parameters associated with D. L of D, which is just the length of gamma. As a path in the graph, every edge is weighted 1. So how many edges do you need to go over the outside of all of this diagram? And you have the area of the diagram, which is just how many triangles you used, number of triangles. So this is a Van Kampen diagram. And what is pi 1? Now I can define to you what pi 1 is. So pi
It's in the triangles.
in the diagram.
Diagram.
Yes, right. Like I actually defined the diagram with no connection to the simplicial complex originally. So it's just you drew triangles in the plane. Just count how many are there. This is the area of the diagram. But actually, it comes from some counting of triangles, but not necessarily distinct triangles, right? The same triangle x1, x3, x4 can also appear here somewhere. x1, x3, x4. But I'm counting how many times how many triangles are in the diagram, not how many inverse images of triangles are there in the original complex.
But also, it's not like you could have drawn any Van Kampen diagram and then filled it out with labels from your complex, because you might run into problems.
Exactly. So this is a very special object.
So it doesn't
Even this special object, it's not clear that you can associate it to a fixed simplicial complex. Yeah, I agree. But when you can, it says something about the simplicial complex. Like this is information about the simplicial complex. Great. What is pi1 of a simplicial complex with some base point? So I always wrote pi1 of y. I'm actually lying. You always need the base point. But again, this is a bit of a technicality. So these are all paths in the one skeleton. The one skeleton. The skeleton of X originating and ending at star. So you collect all the paths that in the graph, just like usual paths in the graph, that start and end at this star position, but you define some equivalence relation on them. So I didn't do it yet. Up to some equivalence relation. What is the equivalence relation? Gamma 1 is equivalent to gamma 2. These are just, again, closed walks in the graph that start and end at star. If and only if you walk over gamma 1, and then you go over gamma 2 to the other side. Okay, so I don't know. This is one path, this is the other path, and they are oriented in some way. So first I walk on the first path according to orientation, then I go on the other path against the orientation. That's very important, but this thing is oriented. This thing has a Van Kampen diagram, has a D such that the circumference of D is exactly gamma 1, gamma 2 inverse. Okay, so if you can draw, gamma 1 is equivalent to gamma 2, if you can draw a Van Kampen diagram associated with this complex such that this is the circumference of this Van Kampen diagram. Is this clear? So it's a weird kind of condition that tells us which paths are the same. And it's when you write it this way, it's not clear that this is a group, but you can check that concatenation of paths is the product of this object. And actually it's a group, like every path, if you concatenate it with the backtrack of this path, it will have a Van Kampen diagram for it. Okay, that's like the first thing you should check, that every element has an inverse. Okay.
Isn't that just us?
What?
Is that just us? Like a single line with every.
Yes, you're right. Like it will look like just a path, and then going back, like it will have no triangles.
Yeah.
Like,
Maybe you can give us an example, like a situation where you think gamma 1 and gamma 2 should be equivalent, and how that relates to the Van Kampen diagram.
So just if you can take the triangle, it's all generated by one triangle taking two edges instead of one edge along the same triangle, right?
Yeah, but these are not closed paths. Let me show you a different one.
No, you can just change them, like
Take a path, add the triangle to it, make it a bit longer. These are
Okay, let's just do it on a tetrahedron, just because I think there it's non-trivial. I claim that going along this triangle and going along this triangle is the same. They are equivalent in the sense, like this is my base point, star. Going around this triangle, you see? The triangle that is closer to us.
You label them and
Yes,
say
let's call this
ABC.
as 1. Okay,
No.
yeah. Star A, B, C. So star A, B, the path star A, B, and the path star AC are star AC. Yeah, what I mean is star AB star, thank you, star AC star, which is this triangle, and the inwards triangle, this triangle. I claim that they are equivalent. How do I do that? So just draw star A, right? Now I need B and C. Yeah, like the point is that I can use the other two triangles to collapse it, but now I need to think, how do you draw the Van Kampen diagram? Yeah, like this is B and this is C, right? So, yeah, but this would not be the circumference. Let's just try to do it brute force-ish, in a brute force manner. star A, B, star A, C, star, right? Can we fill up this thing?
Reverse the second one, right?
Sorry. Yeah. But actually, in this case, it doesn't matter. Like, okay, so it is easy. Okay, sorry. You have a single star. A, B star, A, C. Okay? Here, star A, B, star C, A star. This is the circumference. And here we see two triangles. You could fill up the original two triangles, for example. But I claim there are more interesting Van Kampen diagrams that equate them, that uses the other triangles, for example. So, and another thing, like you can show that the star AC, star AB is just equivalent to doing nothing, to the path that always stays at star. This is also like, this is the identity element of the group. But you can do this, the Van Kampen diagram that just uses this triangle, but you can also add C in the middle. Now you have three triangles in the Van Kampen diagram, right? It's either taking the base of the pyramid or taking the top of the pyramid. And both of them give you a Van Kampen diagram that shows that star AB is equivalent to just staying at star. Yes?
So in the top one, you have star A as like two different edges, that's allowed, or like you can have the edge appearing.
Yeah.
Okay.
It is allowed. Remember, I just need to write down names of vertices.
And it, okay.
They can repeat, clearly they can repeat. Like in the non-backtracking case, yeah, anyway.
No, but if they have an edge, it must be an edge.
Must be an edge,
Yeah, that's yes. Star A is an edge in the original simplicial complex, AB is an edge in the original complex, and so on and so forth. Yeah, sorry. Okay, so,
You should think of the labeling as a simplicial map to X.
Yeah.
yes, exactly.
But you.
Thank you. It must induce, what does it, but it's like in the other way around usually. Like usually the way they do it is they define a map from D as a simplicial complex
Yeah,
to the place. So that's the way you said it. Okay, sorry. So yeah, it's a map. It's equivalent to a simplicial map from D to the original simplicial complex X. Thank you. Yeah, that's a good remark.
I mean, you had all the edges in your complex, right?
In my complexes, yes, but this is well defined even if you don't have all edges in your complex. Yeah. Yeah, I tried to define it to a general simplicial complex X. Maybe that underlying graph is not the complete graph. Great, so this is the fundamental group, and we want to, did I want to say anything else about this before I try to say more? Just a moment.
Say something about like loops and.
Yes, but I already defined everything as loops, but when I have this property that when gamma is equivalent, when gamma is equivalent just to, let's call it star, staying in star in place, this is the property of gamma being contractible. Contractible or null homotopic, it is called null homotopic. This is just a name for us, but it will be important that they use this name at some point. That we did. And what does it mean for pi1 to vanish? So let's just write it as a fact. Let's write it here. Take this slightly down. Fact. Pi1 vanishes, of X vanishes, if and only if every closed path is contractible. It is contractible. So I'm not saying anything about the base point. So you can start from anywhere. Okay, you can draw, if you can essentially find a Van Kampen diagram for every closed path, this is called, this is the same as pi1 vanishing. It's completely equivalent. If your simplicial complex is connected.
So in other words, like, if you have a closed path that you cannot change it through triangles and make it into a point, then that's a non-trivial element of pi1.
Not necessarily, because it doesn't necessarily start at star. So once direction is clear, this direction is clear, this only tells you that those that start in star and end in star have this property. But this is enough if the complex is connected, so there is something to prove here. that if all those that start landed star are null homotopic, then everyone are null homotopic, okay? But it's a simple trick. That's why I called it effect. Okay, great. Now to prove this BHK, so I have 13 minutes. I can handle 13 minutes and say something interesting to you. So to prove this, I said that to prove this, they use the co-isoperimetric inequality. And to prove this, they need to use an isoperimetric inequality. I will say what does it mean to have a hyperbolic group. Okay, so pi1 of a simplicial complex X is, let's just call it hyperbolic. This notion is originally by Gromov, but the equivalence of the definition to this definition, I'm not sure that it's due to Gromov. Like there was a sequence of equivalent definitions that came after Gromov. What?
I think it is.
What I'm going to say is that the original definition, so I'm not sure. I thought he had like the cross product. All the equivalences? I think triangles, for example, is usually denoted to rips, like said to be by rips. But anyway, like I'm not sure about the history, but this is for sure equivalent to what Gromov called a hyperbolic metric space. The pi1x is hyperbolic if there exists a number rho such that the area such that for every, okay, I'm a bit working not in the order that I want. If you have a closed path, for every closed path, say that A of the closed path is infinity if it is not contractible. And if it is contractible, so if it has a Van Kampen diagram, A of gamma is A of D is the minimum over all A of D's such that gamma is the circumference of this Van Kampen diagram. So there is the Van Kampen diagram of this specific gamma that uses the minimal amount of triangles. This will be the area of this specific closed path. So a path is either non-contractible, in this case the area is infinity, or it is contractible and then the area is finite, and the minimum way of doing this is called the area of the curve. Okay? So if for every rho, such that, okay, for every rho, so if there exists a rho such that for every closed gamma, either it is not contractible, so either A gamma is infinity, or A gamma is bounded by rho times length of gamma. Okay, so this is an usual isoperimetric inequality. The area is bounded linearly by the length of the circumference.
And Gromov proved the equivalent.
That this is already equivalent to the other notions. Like this is the most natural, okay, one of the more natural notions that are hyperbolic. Thanks, like, great. So this is what it means to be hyperbolic. And let me just explain to you how is it helpful in this context, okay? So say that you can show me, and this is part of what Babson, Hoffman, and Kale showed, that this pi1 of y is hyperbolic. You try to show that it is non-trivial in this parameter set. The hard part is this. I'll show you the whole proof of this in a moment. I will only wave my hands about this now. So, and this is the interesting part of the paper. This is like 2 pages in the papers, and this is like 20 pages of the paper.
So, Chaim,
Yeah?
you're
Yes?
saying this is a property of pi1?
I'm saying that,
Hyperbolic, the one that's here. Great. But
so, you can say that the simplicial complex is hyperbolic if this is true for any, like, you don't need to write here pi1.
But
this is usually thought of as a property of the fundamental group, but as I define it, it's a property of the simplicial complex.
right, okay.
I'm essentially avoiding the group theory at all.
Now it makes more sense.
Yeah, like the pi one didn't play a role at all here. Yeah, this is just a property of the simplicial complex. Yeah.
Like it's not clear.
But this is equivalent to the fundamental group being hyperbolic. In any other way, Gromov defined it, and the other ways, other people like thin triangles and so on.
If you have gamma 1 and gamma 2 that are equivalent, using this equivalence relation, does it mean something about the area of gamma 1 and gamma 2? Like,
Yes, tell you something. It bounds the amount of triangles you need to do to prove that. That's the whole point. What hyperbolicity tells us? Say that I want to prove, what does it mean to prove that pi 1y is with probability 0 trivial? It means find some path which is not contractible. Okay? And the easiest path you can think of is just one of the length 3 paths in your original complex. So what Babson, Hoffman, and Kale show is that let's look at the following path in the simplicial complex. 1, 2, 3. Clearly, the probability that you actually plug in this triangle tends to 0 when n tends to infinity, right? Because in this parameter setup, this is clear. So at least area 1 triangulation tends to 0. And you can try to say, okay, let's do some union bound. How would you do a union bound? You would say, okay, let's look at all triangulations with area 2. Let's look at all triangulations with area 3. Let's look at all triangulations with area 4. But if you try to do this union bound, this is an infinite union, and you will tend to infinity, right? Like so, you won't be able to do a union bound this way. Isoperimetric inequality gives you a way of you doing a union bound. So if you know that you have this property, you don't need to check all possible triangulations of 1, 2, 3. You just need to select the finite amount, which is bounded by 3 times rho. Okay? So at least that's not the way they do it. They need to do something more intricate. Okay? But at least heuristically, how can hyperbolicity help you? It can at least reduce you from an infinite search space of possible triangulation to a finite search space of possible triangulations. You don't need to like now refute an infinite amount of possibilities, just a finite amount.
But
So I hope that
it's
this.
also the work that is hyperbolic in this regime.
Yeah. It's not only like that's the proof. The main part of the proof is proving that this is hyperbolic in this regime. Yeah. And this is very similar. I'll just say that they're not the first to do such a thing. Like Gromov originally defined a notion of random groups. And the way he showed that his random groups are non-trivial in some parameter setup is exactly by showing that they are hyperbolic. That's the way Gromov did it already. And then Zhuk came and did for another model called the triangular model, again, the same thing. So it's like the third time this type of thing happens, you define a model for random groups, and the way you show it's non-trivial, so the way you show something satisfies this condition, it is exactly by first showing that the group is hyperbolic with probability approaching 1, and then using this hyperbolicity to show that there are non-contractible paths. This is like like this proof structure is not due to Babson, Hoffman, and Kale, but they needed to like it's a different model, so the way to do it is different. Like, I'll just say this is a paper from JAMS, like it was highly regarded, and it is still highly regarded. It's a very although like the proof philosophy is very similar to previous proofs, it's still
It's very different from the proof of the triangular model.
Yeah, it is different. It's very different. And the triangular model is when you take the delta complex, instead of the full complete complex on n vertices, a single vertex, but all possible triangles that start and end on this specific vertex. And you can see that, for example, if you check the densities, they're not compatible. So the place where they think about it, that's exactly my point. The triangles are not 3 edges. They're not 3 uniform edges. The triangular model is like just add the relation, take the product of 3 random edges. That would be like the analog of the triangular model. And here, like there is some more restriction. So you should think of it like you're not allowing to sample all possible length 3 words. You're only sampling very specific type of words of length 3.
Yeah, but the function is the same function.
No. You.
It's about root 10, right?
What?
It's root 10.
Yeah, no. But the proportion, you say how many relations do you need to add?
It's the same. We want the links to be an expander. It's the same. Yes?
No. Links expanders is T. Like you're missing. When do you kill pi one? It's actually in a different position.
Sorry.
No. It's a genuinely in a different position. These are different models, and they needed different techniques. Like I want to. I think when you say only the philosophy, when you mumble like I mumble now, that you use hyperbolicity, this is very standard. Okay, Gromov made it very standard. That you use hyperbolicity to show that pi one does not like vanish. But still, like they needed to do both the proof of hyperbolicity here is very different, and they need to do very careful analysis.
But that's like,
and it's a different model than Jukes.
that's the crux of it, right? Like if you look at why this like random simplicial complex, then you need to somehow show that it is hyperbolic, and then you can use your union bound.
So they again, what they actually do is they don't recover a union bound after. They do again something slightly more complicated. But in spirit, why hyperbolicity help you? It recovers like from an infinite search space to a finite search space, and now you can only handle like something which is bounded, and then they handle this something bounded not by a union bound, but by another trick. That's the way you should think about it.
The point is that once you prove that whatever you got is hyperbolic,
you're left with something manageable.
Then
You're left with like hyperbolicity is the hard part.
And how do you prove hyperbolicity?
That's a very good question. I want to tell you as much as I can in the 2 minutes that I have. But essentially what they do is the following. Think about it. We think of expansion in two ways. If you take a set, it is well connected to the complement. But also a way of thinking about it is if you take a set, it is weakly connected to itself. Right? There are not many edges inside that. Let's think of the regular graphs, okay?
Like the small.
Yeah, at least I'm only talking about the small regime. Like in the small scale, like you behave like a tree, like you behave like, right? Like that's the type of way you think about expansion. You have the same thing here, and that's what they do. If you look at small collections of vertices in your random simplicial complex, there are not many triangles there. And only by this observation and many deep topological things, so the only place that they use randomness is that the small scale behavior of these simplicial complexes are sparse. Like locally, they don't have many triangles. If you take a collection of triangles and you look how many vertices do they touch many vertices. Okay? And from this property, which is the only property that they need from randomness, they automatically deduce hyperbolicity. This is a sufficient condition for hyperbolicity.
This is what you were calling the isoparametric behavior that they use, or this is something else?
No. This is a fact that you can convince yourself that a random complex will have, right? That like if you fix a small collection of triangles, they will touch many vertices.
This is the notion of expansion.
Yeah, it is. I agree. Like the fact that on the small scale you behave that way is a notion of expansion. And that's all they need from the random model. Once you deduce that, they just prove three theorems that are completely deterministic. Just if you have satisfied this condition, then you're hyperbolic. If you satisfy this condition, then the path 1 to 3 is not contractible. Like they do all these things and they moved all the problem into the actual doing algebraic topology. So they do some induction. For example, if you have these sparse, they call it sparse complexes, such that every subcomplex on the triangles touch at least double the amount of vertices, okay? So I'm saying it out loud. Then, for example, the homotopy type of this complex must be a wedge of circles, spheres, and projective planes. So they actually give you like topological data out of this sparsity condition, which is completely general. It's just a theorem, but no randomness involved. But this is deep, like this is some induction, and it goes, you need to get out of the model of simplicial complexes, you need to define some more general notion of cell complexes that they use, and so on and so forth. Like now we need to work, but I don't want to talk about it because this is more algebraic topology, and I think like it would be hard for us to go through, for example, this induction. But that's the type of argument that they do. And I will just say on the other side, so I said something about this, that you do use hyperbolicity and some like actual algebraic topological type of arguments on the sparse complexes that you get in when you sample a simplicial complex. For one, I will just say that in this parameter range, the link of a vertex, so usually we denote it y of v, the link of a vertex v, intersection with the link of the vertex w. So the link of a vertex v in the lineal Meshulam complex is exactly gn minus 1p. So this is just gn minus 1p. Each one of them. But this is independent events. So if you fix two vertices, you put all the other vertices in the middle, the probability that this triangle is included is independent than the probability that this triangle is included. So this intersection behaves like gn minus 2 t squared. This is sampled according to this. And if you take it in this parameter range, all the intersection of links are connected. And that's why 3 log n divided by n plus omega n plays a role. This is exactly the parameter range where the intersection of all these links are connected. And when the intersection of all the links are connected, you can just, by force, triangulate each triangle in the original graph. So 1, 2, 3, for example. You look at the link of 1 and the link of 2. At least one triangle touches 1, 2, right? So there is some W such that 1, 2, W is in your simplicial complex. And now if in the link you connect 3 to W, you exactly get this type of triangulation. They just brute force show you that every path of length 3 is triangulated once the intersection of links is connected. So that's like the easy part of the paper.
This is only checking triangles, not every.
That's in the what? Yeah. That's a good argument. That's a good remark. Convince yourself that once you can triangulate any triangle, you can triangulate every closed path. Yeah, you're right. It's not trivial. It's not trivial.
Yeah, every triangle with a constant number. Yeah.
All the triangles, all the length 3 paths.
Yeah.
Once you contract all length 3 paths in your graph, you can contract all other lengths. Yeah.
Okay. Yes.
Like this is very related to the fact that now you behave essentially like the complete complex, and that pi1 of the complete complex is trivial. Okay, so but you're right that it's not obvious that this is enough. Yeah.
How did they shape the log n?
How did they shape? They found more intricate ways of triangulating paths. So they find more you mean Linial and Peled? Luria and Peled?
Yes.
The way Luria and Peled shape the log n is that they don't assume the connectivity of the intersection. They find much more complicated triangulations of every path of length 3. So it's a much deeper result. This is genuinely what I said. It's a one page, and you just need to convince yourself that the intersection of links is connected. Yes.
So I also want to ask, how do you use this hyperbolic property to improve the union bound?
Just think about it as follows. I want to convince you that 1, 2, 3 is not contractible.
Yes.
How can it be contractible? Let's think about it. It can be contractible where you find the Van Kampen diagram of area 1. It can be contracted when you have a Van Kampen diagram of area 2 and 3 and so on. The whole point is that once you have hyperbolicity, you at least move from this infinite search space of possibly any size of area to a finite collection.
It's a union bound over all possible hypothetical then diagram.
With some bound on the number of triangles, and thus it's finite. So again, I'm lying here a bit, but
why the linear relation will
you're right that any relation seems.
No, you have a probability.
No. He's asking why did I need what's the problem with having a square here?
It's a big problem of having a square because the probability of this triangle existing in you need the labeling to come from the actual complex.
But you're only using this for paths of length 3 anyway, so you're
right that it doesn't seem clear, and that's why I'm saying that I'm also lying, that this is the only place that where they don't really do the union bound, they do something more intricate.
It's because union bound doesn't.
But I wanted to give you like at least, I don't know that union bound works. I tried to think about it myself. I wasn't able to just finish the proof just by using a union bound. I think it doesn't work. Like I think you genuinely need something extra, and they do use something extra. But I tried to give you, you're right, I'm lying. Like, it's not as if this is enough, and it's not clear from the way I did it that having a quadratic relation is not enough, like, because you're looking only on the path 1 to 3.
You do a union bound not just on the delta, on the labeling, right? There's the union bound over all labeling. That if it was not linear, it wouldn't work.
Okay, like Avi automatically sees something that I probably don't see.
I remember something from Gomer's paper.
No.
Yeah, okay, in Gomer's paper it's different, like I'm not sure.
Yeah, I don't understand the comment. He's saying something about proving this general property, but then a priori you're only using it for paths of
No,
length
you
3.
prove it.
So why do you care if it's length 3
No,
squared?
But that's the whole point where this model is different from the other models.
I think you prove it for every length. You fix a length.
Yeah, this thing is for every length.
No, you
No,
prove
I
it
know.
for every length. But the
Yeah.
question is, why don't you just use it for length 3, for just paths that are triangles? Right?
Yes.
I mean, if you can't use it for a triangle, then
How?
So the truth is that you have two things that you need to show. That the probability that 1, 2, 3 is contractible, it has two, you can bound it by the probability that 1, 2, 3 has area larger than 3 rho, plus the probability that 1, 2, 3 has area smaller or equal to 3 rho. This is clearly killed by hyperbolicity, and here you need to do something else. And I kind of tried to convince you that you maybe want to do this by a union bound. I claim that's not what they do. I don't think it works. I try to give you an impression of why this is already a big step. Like, this is a much easier parameter to handle than to handle both of these things. Once you're hyperbolic, you kill this probability. You only need now to kill this, and this they do by, again, some algebraic topological type of arguments that understand the topology of these spaces, like the fact that they are wedges of circles and spheres, and they count in this wedge of circles, spheres, and projective planes, what is the size of the triangulations in there, and they give some bounds using the, how is it called? The Euler number and stuff like that. Like, they do work. Like, it's not, I kind of lied and say, okay, from here you can do a union bound. That's not really true.
Why union bound works?
No. Now union bound, you can at least try to do a union bound, because the number of triangulations of a path of length 3 bounded by 3 rho, it's at least a finite amount.
Yeah, but it's.
You can ask for each one of them.
And to the nine row, like it's.
Yeah.
Killed by probability.
You're right. That's what I said, that like, it doesn't work, but at least in spirit, yeah, I need to finish. Let's finish. But you handle these both terms differently. That's it, that's right.
All right, thank you very much.